definition.
It will be a half of half, then
just give me the number.
It's
Is it 10? Who said 10 first? Great. Yeah, let's give a round of applause. The most mundane and routine way is to build something like a square over here. Actually, this is going to be rectangular. Then build some rectangles over here. And chip off all these areas of all of these rectangulars. But also there is a different way. If we look at these two vectors, vector A and vector B, and we find the determinant of that, this is going to be exactly the area of this parallelogram. Step 4. Determinants of n by n. First we get with the simple matrix which is 2 by 2, and the matrix is A, B, C, and D. So the determinant of that is going to be AD minus BC, and we all know that. The second is used for the matrix 3 by 3. This is what we call Serre's rule. So if the matrix looks like A, B, C, D, E, F, G, H, I, then we just add 2 columns over here or 2 rows over here, and the rule is how we get the signs right. So this is A, B, C, A, B, G, E, F, G, E, G, H, I, G, H. And then basically the products along those lines are going to be plus signs. The products along those lines are going to be minus signs. So we may use the Serre's rule to find the determinant of this matrix. So I think you can tell me what this determinant is pretty much immediately. Why? correct. Because yes, you can use the series rule, you can use the rule of triangles, or whatever rule you can, but actually you can see that this matrix consists of three vectors, C1, C2, and C3. And you can see that C3 is equal to 3 times C1. Which brings us to the linear dependency. That means the linear dependent. And since they're linear dependent, this factorial is equal exactly 0. So this is again something of the recollection theory. Now we are going back to the linear systems. And here we would like to recall the rule, which is called the Cramer's rule, and again something that you should have studied and probably remember well. So if we have matrix A, which is 2, 1, 3, 2, and matrix B, which is just 1 and 1, and you have to solve the equation AX equals to B. So the first way is the one that I have shown before, which is X is equal A minus 1 to the B. And here, this one is going to be, if we use the same rule, we have 2 and 2 replaced, so we have 2 and 2. 1 and 3 change their signs. This is minus 1 minus 3. The determinant of this matrix is 4 minus 3 is 1, so we don't have to multiply by anything else. 1, 1 here, and we have 1 minus 1. This is the first way, however, this is way A. The second, way B, is use the Cramer's rule, and here we have to determine a bit more determinants. The first determinant is when we substitute this column into this matrix, which is basically means this is 1, 1, 1, 2. So this one is equal to 1. The second determinant, we can call this auxiliary determinant, but again, this is another fancy term that you don't have to remember, so it's just some other determinant. We put this column into this, instead of this column in the matrix, so this one is 2, 3, 1, 1. This one is equal negative 1. And the Cramer's rule is x1, x2 is equal to determinant 1 over the determinant of the first matrix, determinant 1, determinant of the second matrix. So again, we come to the same 1 and minus 1. Which method to use is up to you. The only thing that I would like to tell you is the greater is the size of the matrix, the easier it is to use this Jordan-Gauss elimination method. Because all of those other methods, they are going to be very long. Because now if you have to calculate the determinant which is 2 by 2, you can do it by hand. If you, just in your mind. If you have to find the determinant which is 3 by 3, this is also quite easy. If it comes to determinant something like 5 by 5, the number of arithmetic operations is much higher if you use the Cramer's rule compared to this Jordan-Gauss elimination method. And actually, Jordan-Gauss elimination method is what is used in the computers when they calculate all these equations. Now a very short one, which is 6, is the linear independence.